Hello, all cosmic explorers, and welcome back to our journey through the mystery of universes. Look up at the night sky, and you are witnessing the echoes of unimaginable power. Stars, billions of them, shine with steady brilliance. But sometimes a star doesn't just shine, it explodes. Not just an explosion, but a supernova, an event so cataclysmic that for a brief period, one single star can outshine the entire galaxy. The supernovae are critical. They forge the heavy elements essential for planets, for life, for us. There are cosmic lighthouses helping us measure the vast distances across the cosmos. But for all their importance, there are still deep mysteries surrounding these stellar deaths. And today we are diving into one of the most mind-bending theory out there. Could the universe's tiniest, most ancient black holes maybe unexpected spark for some of these grandest explosion? Could primordial black holes be the universe's ultimate time bombs, igniting the Type 1a supernovae? Type 2 supernovae are relatively straightforward. This happens when a massive star, many times the size of our sun, runs out of the nuclear fuel. Its core collapses under its own immense gravity, rebounds, and detonates in a spectacular fashion. Think of it as a star dying alone, under its own weight. We understand this pretty well now. But there are these Type 1a supernovae. These are different. They always involve a white dwarf, a super dense Earth sized remnant of a star like our Sun, after it has shed its outer layers. White dwarfs are essentially stellar embers slowly cooling. They are stable, inert, they shouldn't explode on their own. For a Type 1a supernova to occur, a white dwarf needs a trigger. It needs to gain enough mass to reach a critical limit called the Chandrasekhar limit, about 1.4 times the mass of our Sun. Once it hits this threshold, it becomes unstable, and runaway thermonuclear fusion ignites in its core, leading to a brilliant, uniform explosion. This uniformity is precisely what makes them so valuable as standard candles for measuring cosmic distances. That is what what humans are doing and using them. The accepted wisdom is that this mass gain happens when a white dwarf is in a binary system siphoning material of a companion star. This is the single degenerative model, or perhaps two white dwarfs in a binary system merge, the double degenerate model. These models explain most Type 1a supernovae, but are they the whole story? What if there is a different, more exotic trigger at play for some of these stellar fireworks? This is where our tiny time bomb enters the stage, which is also known as the primordial black hole, or PBH. Forget the massive black holes we usually talk about. The supermassive ones at the center of the galaxies, or the stellar mass ones formed from a collapsing star. The primordial black holes are entirely different. They are the hypothetical black holes that formed not from a stellar collapse, but in the chaotic, incredibly dense conditions of the very early universe, a mere fraction of a second after the Big Bang. Imagine a universe so compressed, so hot, and so dense that the tiny fluctuation in its fabric could have been powerful enough to squeeze regions of space-time into black holes without any stars required. These PBH could theoretically come in a vast range of sizes, from smaller than an atom to potentially thousands of times the mass of our Sun. Crucially, many scientists theorize that if they exist, PBH could make a significant portion of the dark matter. We know dark matter exists because of its gravitational influence on the galaxies, but we cannot see it or detect it directly. It doesn't interact with light. PBH, being the black hole, would fit that description perfectly. They are dark, They are massive, and they exert gravity. So if these cosmic relics are indeed floating invisibly throughout the universe, could they be doing more than just providing gravitational scaffolding for galaxies? Could they be interacting with the stars in unexpected catastrophic ways? Let's connect these two fascinating concepts: white dwarf and the primordial black holes. Imagine a rogue PBH, perhaps the size of a small asteroid, drifting through space. It's incredibly dense with the mass of a planet, but packed into a tiny invisible sphere. Now picture this PBH encountering a white dwarf star. This isn't a guaranteed event, but given the sheer numbers of the white dwarfs and the potential abundance of the PBH, it is statistically possible over the cosmic timescale. As the PBH gets close enough, the white dwarf immense gravity captures it. The PBH doesn't just pass by; it enters into an orbit around the white dwarf, a deadly cosmic dance. But a black hole, no matter how small, is powerful gravitational force. For eons, through gravitational radiation and the interaction with the white dwarf's plasma, the PBH orbit would slowly, decay. That means it will start falling into the white dwarf. It would spiral inwards, getting closer and closer to the white dwarf's core. This is where the real drama begins. As the PBH plunges deeper into the white dwarf, it starts to consume the star from the inside out. It's accreting material. This accretion process, where matter falls into the black hole, releases enormous amount of energy, primarily in the form of heat. Think of the incredible temperatures and pressure being generated in the immediate vicinity of this tiny, ferocious black hole deep within the white dwarf. The white dwarf, remember, is made of degenerate matter. It is like a giant atomic nucleus. The heat and the pressure from the spiraling, accreting PBH would eventually become so intense, so overwhelming that it would trigger a runaway nuclear reaction in the core of the white dwarf. This isn't just a slow burn, this is a thermonuclear ignition we discussed earlier. The exact same process that happens when a white dwarf reaches the Chandrasekhar limit by accreting from a companion star. But in this scenario, the trigger isn't the external mass gain, it's an internal time bomb, the primordial black hole releasing energy and heat directly in the core. The result? A type 1a supernova. A spectacular cosmic explosion, all initiated by an invisible ancient black hole no bigger than a city. The PBH ignition theory, while still speculative, offers some compelling advantages for astrophysicists. Firstly, it could solve the problem with type 1a supernova. While the binary accretion model works well for many cases, there are still some type 1a supernovae for which we haven't found a clear companion star or merger of white dwarfs. The PBH model offers an alternative ignition mechanism that doesn't rely on stellar companions. Secondly, it provides a fascinating link between the largest explosion in the universe and one of its most fundamental mysteries of the dark matter. If the PBH are indeed a significant component of the dark matter, then observing their effects even indirectly through supernovae would be a monumental discovery. It would be an elegant way to detect something we otherwise cannot see or interact with. However, like any other radical scientific theory, it faces significant challenges. The probability of white dwarf capturing a PBH and the PBH being in the right mass range to cause ignition rather than just harmlessly passing through or immediately consuming the star is very low. It's a cosmic needle in a haystack problem. Detecting direct evidence of PBH inside a white dwarf before it explodes is currently beyond our capabilities. We would have to rely on subtle gravitational wave signals or unusual pre-supernova phenomena, which we haven't observed yet. Scientists are constantly refining models and looking for specific signatures that would distinguish a PBH ignited supernova from more conventional ones. Could there be a subtle difference in the light curve, the elemental composition of ejecta, or the presence or an absence of a companion star after the explosion? These are the questions researchers are actively exploring. If this theory holds even for a fraction of type 1a supernova, the implications are enormous. Our understanding of the standard candle could be refined. If some type 1a supernova have different ignition mechanism, even if they appear similar from far away, it might subtly affect our measurements of the cosmic expansion and the age of the universe. This would be a crucial adjustment of our cosmic distance ladder. More profoundly, it would give us a concrete avenue to explore the nature of dark matter. The existence of PBHs isn't just about supernovae, it ties into the very fabric of the early universe, providing clues about its initial conditions and the physics that governed it. The search for primordial black hole is a vibrant field in astrophysics. Scientists are looking for them through various means. Things like gravitational lensing, gravitational waves, and gamma ray burst, which includes exploding primordial black hole if they are small enough and could theoretically produce tiny energetic bursts. And now potentially supernovae signatures. Looking for these subtle differences in type 1a explosions that might point to an internal PBH trigger. Each new observation, each refined model bring us closer to understanding whether these ancient invisible time bombs are truly shaping the cosmic landscape in such dramatic ways. So, are the primordial black holes igniting the supernovae? The honest answer is we don't know yet, but it is truly exciting possibility. It's a testament to the scientific process, challenging established ideas, proposing new ones, and relentlessly searching for the evidence. The universe is a place of profound complexity and beauty, where tiny ripples in space-time from the Big Bang might dictate the violent death of stars billions of years later. It's a reminder that even the most well-understood phenomena can harbor deeper and stranger secrets. Whether through direct observation or indirect clues, like the violent demise of the white dwarf, the hunt of primordial black hole continues, and with it, our quest to unravel the true nature of dark matter and the spectacular engine of the cosmic creation and destruction. So, what do you think about the idea of primordial black hole as supernovae trigger? Let us know in the comments below. And if you found this cosmic journey intriguing, please hit that like button, subscribe for more adventurous astrophysics, and ring the notification bell so you don't miss out our next deep dive. Thank you for joining live today and joining me in exploring the universe's tiniest time bomb. See you next time. Until then, keep looking up and keep wondering.